On October 19, 2017, astronomer Robert Werrick sits before his computer screen at the University of Hawaii, examining images captured by the Pan-STARRS telescope the night before. The automated system has flagged something unusual, a point of light moving against the background stars, but not in the familiar elliptical dance of asteroids or comets bound to our sun. This object moves with the straight-line trajectory of something passing through, something that belongs to the spaces between stars. The discovery appears first as a series of pixels, barely distinguishable from cosmic noise, like a ghost materializing from the digital static of deep space observation. Over the following hours, as more observations accumulate across observatories worldwide, the truth emerges with mathematical certainty. The object approaches from the direction of the constellation Lyra, traveling at 26 kilometers per second relative to the Sun, far too fast to be gravitationally bound to our solar system. It has already passed its closest approach to our star and now races outward toward the constellation Pegasus, carrying with it the first confirmed evidence that objects from other stellar systems regularly visit our cosmic neighborhood. The velocity alone tells a story written in Newton's equations, a signature of gravitational freedom that speaks of origins in distant suns. Scientists assign it the designation 1Y Oumuamua, marking it as the first officially recognized interstellar object. The Hawaiian name means scout, or messenger from afar arriving first, chosen by the Pan-STARRS team to honor the observatory's location atop Haleakala, where ancient Polynesian navigators once studied the stars to guide their journeys across Earth's vast ocean. Now their descendants in spirit track a different kind of voyager, one that has crossed not water, but the incomprehensibly larger ocean of interstellar space. Yet, even as astronomers celebrate this historic discovery, a puzzle begins to unfold in the reflected light captured by their instruments. Initial observations suggest Oumuamua reflects sunlight in a pattern consistent with an asteroid, rocky and metallic, rather than icy like a comet. Its spectrum shows the reddish tint of oxidized metals, similar to objects found in the outer asteroid belt between Mars and Jupiter. But asteroids, formed in the warm inner regions of planetary systems where rocky planets coalesce, should not survive the million-year journeys between stars. The cosmic radiation and occasional stellar encounters should have ground them to dust long ago, leaving only the hardier icy bodies to traverse the galactic void. The object tumbles through space in a complex rotation, completing one full turn every 3 hours. Its brightness varying by a factor of 10 as different surfaces catch and reflect sunlight. This dramatic variation suggests an extremely elongated shape, perhaps 10 times longer than it is wide, like a cosmic cigar or needle threading through the solar system. No known asteroid or comet exhibits such extreme proportions, adding another layer to the mystery of this interstellar messenger. The rotation itself tells a story of ancient violence, likely the result of a collision that sent Oumuamua spinning into the void eons ago. Its tumbling motion, a fossil record of that primordial impact. As telescopes around the world turn to track this visitor, astronomers piece together its recent trajectory through the solar system. Oumuamua approached from the north, diving down through the plane where the planets orbit, swinging around the Sun at a distance closer than Mercury's orbit, then climbing back up and outward toward interstellar space. Its path traces a hyperbolic arc, the mathematical signature of an unbound orbit, a trajectory that speaks of speeds too great for our Sun's gravity to capture and hold. The timing of the discovery carries its own quiet irony. Oumuamua has been visible to Earth-based telescopes for only a few weeks when Werrick spots it, and it was already past its closest approach to the Sun. Had it arrived a few decades earlier, before the advent of automated sky surveys and sensitive CCD cameras, It would have passed through our solar system completely unnoticed. One more messenger from the galaxy that delivered its secrets to empty space. Had it been discovered a year earlier, when it was still approaching the Sun, astronomers would have had months rather than weeks to study it in detail. The object's small size compounds the challenge of observation. Estimates based on its brightness suggest Oumuamua measures perhaps 400 meters at its longest dimension, smaller than most city blocks. A cosmic pebble, barely visible even to the most powerful telescopes. At the distance of the outer planets, it appears fainter than the dimmest stars visible to the naked eye under perfect dark skies. Yet this tiny visitor carries within its physical structure and chemical composition the story of another stellar system, another family of planets orbiting a distant sun. As Oumuamua speeds away from the Sun at 44 kilometers per second, astronomers realize they have perhaps weeks before it fades beyond the reach of even the most powerful telescopes. The race begins to extract every possible piece of information from this fleeting visitor, this first tangible evidence of the vast population of objects that drift in the darkness between stars. Radio telescopes scan it for any artificial signals, though none are detected. Spectroscopes analyze its reflected light for clues to its composition. Photometers track its rotation and brightness variations to deduce its shape and surface properties. The mystery deepens with each observation. Oumuamua shows no signs of the gas and dust coma that typically surrounds comets as they warm near the Sun, yet its apparently rocky nature seems inconsistent with survival during interstellar travel. Its extreme elongation has no precedent among solar system objects, suggesting either unusual formation conditions or perhaps partial fragmentation during its long journey through space. The scientific community begins to grapple with the realization that their first close look at an interstellar visitor has raised more questions than it has answered. Only took 4.5 billion years for one to finally announce itself to human science. Only lasted a few months in our telescopes before vanishing forever into the cosmic deep. Only left behind more questions than answers about the nature of interstellar space and the objects that call it home. Word count: Chanchiwin 1593. The shape of Oumuamua emerges slowly from the mathematics of light, assembled from photons that have traveled across interstellar space to strike silicon detectors in Earth-based telescopes. As the object tumbles through its 7.3-hour rotation cycle, its brightness oscillates with mechanical precision, dimming and brightening as different faces present themselves to the Sun. The amplitude of this variation, a tenfold change in reflected light, tells astronomers they are witnessing something unprecedented in the solar system's catalogue of known objects. Traditional asteroids and comets exhibit brightness variations of perhaps 2 or 3 times as they rotate, their roughly spherical or moderately elongated shapes casting familiar patterns of shadow and illumination. But Oumuamua's dramatic light curve suggests an object stretched to extraordinary proportions, like a cosmic splinter or shard tumbling end over end through the void. Computer models, fed with the observational data, converge on a shape ratio of roughly 10 times longer than it is wide, resembling a metallic cigar or perhaps a flattened disc viewed edge-on. The precise geometry remains tantalizingly uncertain, hidden behind the ambiguities of distant observation. Light curve analysis can distinguish between a long, thin cylinder and a flat pancake-shaped object viewed from certain angles, both of which would produce similar brightness variations as they rotate. The lack of detailed imaging. Oumuamua appears as nothing more than a point source. Even in the largest telescopes forces astronomers to rely on these indirect measurements, like archaeologists reconstructing an ancient artifact from shadows cast on a cave wall. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Program leads one of the teams analyzing Oumuamua's rotation and shape. His colleagues spread across multiple continents coordinate observations, each telescope capturing a few precious hours of data before Earth's rotation carries Oumuamua out of view. The international collaboration unfolds with quiet urgency. Scientists sharing data and preliminary results through encrypted channels, knowing that every passing day carries their target farther from the Sun and deeper into observational obscurity. The object's surface properties add another layer to the puzzle. Spectroscopic analysis reveals a reddish coloration similar to objects in the outer solar system, Kuiper belt bodies and trojans that have been darkened and reddened by eons of cosmic ray bombardment. This organic-rich patina suggests Oumuamua has indeed spent vast periods exposed to the radiation environment of interstellar space, its surface slowly cooking under the influence of galactic cosmic rays and ultraviolet starlight from distant suns. Yet the surface shows no signs of the volatile ice's water, carbon dioxide, methane that astronomers expect to find on objects originating in the cold outer regions of planetary systems. As Oumuamua approached within 0.25 astronomical units of the Sun, closer than Mercury's orbit, it should have heated to temperatures sufficient to sublimate any surface ices into visible gas clouds. Comets routinely develop spectacular comas and tails under such conditions, their icy nuclei boiling away to create the ethereal displays visible from Earth. Oumuamua remains stubbornly inert, showing no signs of outgassing despite temperatures that should have activated any volatile materials on its surface. The rotation period itself carries information about Oumuamua's structural integrity, an object tumbling at 7. 3 hours approaches the limit of what a loose rubble pile held together by weak gravity can sustain. Faster rotation would overcome the gravitational binding and scatter the constituent pieces into space. This suggests Oumuamua possesses sufficient structural strength to maintain its integrity under rotational stress, either a single coherent piece of rock and metal, or a rubble pile bound by forces stronger than simple gravitational attraction. Computer simulations attempt to trace the object's origin story written in its current rotation state. The tumbling motion likely results from a violent encounter in its distant past, perhaps the collision that ejected it from its parent system, or a subsequent impact during its journey through interstellar space. The specific orientation of the rotation axis, tilted with respect to its orbital motion, preserves a fossil record of that ancient trauma, like a wine bottle spinning through space, still carrying the motion imparted by some primordial catastrophe. As observations accumulate, astronomers begin to appreciate the statistical miracle of Oumuamua's discovery. Objects of its size, traveling at interstellar velocities, spend only a few months within the detection range of current sky surveys. The vast majority pass through the solar system unnoticed, too small and fast-moving to trigger automated detection algorithms designed primarily to track potentially hazardous near-Earth asteroids. Estimates suggest that several interstellar visitors of Oumuamua's size pass through the inner solar system each year, invisible messengers carrying stories from distant worlds that remain forever untold. The elongated shape itself challenges theories of planetary system formation and evolution. No mechanism in current models produces such extremely stretched objects during the normal process of planet formation. The shape suggests either exotic formation conditions in Oumuamua's original system or significant modification during its interstellar journey, perhaps partial fragmentation that stripped away portions of a larger parent body, leaving behind this elongated remnant. Radio telescopes at the Green Bank Observatory in West Virginia and Parkes Observatory in Australia scan Oumuamua across multiple frequencies, searching for any artificial signals that might suggest technological origin. The search for extraterrestrial intelligence receives its first opportunity to examine an object confirmed to originate from another star system. The radio silence that emerges from these observations eliminates exotic explanations while deepening the natural mystery of this interstellar wanderer. Only took a few dozen photons reflected from its surface to reveal its strange geometry. Only needed a few weeks of careful measurement to establish its unprecedented elongation. Only left astronomers to wonder whether such shapes represent common products of interstellar travel or hints of formation processes unknown in our own solar system. The tumbling rhythm of Oumuamua creates a temporal signature as precise as a cosmic metronome, its 7.3-hour rotation cycle marking time across the emptiness of space. Each complete turn brings different faces of the object into sunlight, creating the predictable rise and fall of brightness that allows astronomers to track its orientation despite the vast distances involved. The rotation itself becomes a kind of clock, measuring the passage of time not in Earth hours, but in the slow pirouettes of an interstellar visitor spinning through the void. Observatory after observatory captures this rhythmic dance of light and shadow. The Lowell Observatory in Arizona records the object's brightness variations through multiple filters, each wavelength of light revealing subtle differences in surface composition across Oumuamua's elongated form. The European Southern Observatory's Very Large Telescope in Chile adds its observations to the growing dataset, its adaptive optics systems compensating for atmospheric turbulence to extract the faintest possible signals from this distant target. Telescopes in Hawaii, Spain, and California contribute their own measurements, creating a global network of observation that follows Oumuamua across Earth's rotating sky. The rotation period of 7. 3 hours places Oumuamua near the theoretical limit for a gravitationally bound rubble pile. Objects spinning faster than this critical threshold would overcome their own weak gravitational attraction and disperse into space, their constituent rocks and dust scattered along their orbital path. This suggests that Oumuamua possesses either sufficient internal structural strength to resist rotational disruption, or perhaps represents a single coherent piece of material rather than a collection of smaller fragments held together by gravity alone. Tupet, Olivier Hainaut at the European Southern Observatory coordinates much of the photometric analysis, his team developing sophisticated models to extract maximum information from the limited observational data. The light curves they construct reveal not just the rotation period, but hints about the object's three-dimensional shape and the distribution of material across its surface. Dark and light regions create subtle asymmetries in the brightness variations, suggesting a heterogeneous composition that varies from one end of the elongated object to the other. The tumbling motion itself carries information about Oumuamua's violent past. Unlike the planets and moons of our solar system, which generally rotate in stable, predictable patterns aligned with their orbital motion, Oumuamua tumbles chaotically around multiple axes. This complex rotation suggests it was set spinning by some ancient collision or gravitational encounter, its current motion a fossil record of primordial violence frozen into its mechanical behavior. The specific orientation of the rotation axis, tilted at a steep angle relative to its orbital plane, preserves evidence of the forces that first sent it tumbling into interstellar space. Computer simulations attempt to model the physical processes that could produce such rapid, complex rotation in an interstellar object. Planetary ejection scenarios, gravitational encounters with massive planets that fling objects out of their parent systems, typically impart significant angular momentum to the ejected bodies. Close encounters with stars during the interstellar journey could further modify the rotation state, though such encounters remain statistically rare during the million-year timescales of interstellar travel. The current rotation of Oumuamua thus represents a kind of mechanical memory, preserving information about its dynamical history written in the language of angular momentum and rotational energy. The brightness variations also reveal subtle color changes as different faces of the object rotate into view. Spectroscopic analysis shows that Oumuamua's surface exhibits slight compositional variations, with some regions appearing slightly redder than others. This heterogeneity suggests either an originally diverse composition or the effects of space weathering processes that have modified different parts of the surface to varying degrees. Cosmic ray bombardment, solar wind particle impacts, and micrometeorite erosion all contribute to the gradual alteration of surfaces exposed to the interstellar medium. Attempts to detect any wobble or precession in the rotation prove unsuccessful, suggesting that Oumuamua rotates as a relatively rigid body rather than a loose collection of fragments. This mechanical stability supports models of the object as either a single piece of solid rock and metal or a rubble pile bound together by forces beyond simple gravitational attraction, perhaps cohesive forces between constituent particles, or structural strength inherited from a larger parent body that was subsequently fragmented. The precision of the 7-3-hour period allows astronomers to predict exactly when Oumuamua will reach maximum and minimum brightness, enabling coordinated observations across multiple wavelengths and observation sites. This temporal predictability becomes crucial as the object fades with increasing distance from the Sun, allowing observers to concentrate their limited telescope time during the brief windows when the object presents its maximum surface area to both solar illumination and Earth-based detection. Temperature models based on the rotation rate suggest that Oumuamua's surface experiences dramatic thermal cycling as it tumbles through space. The elongated shape means that different parts of the object receive vastly different amounts of solar heating depending on their orientation relative to the Sun. During each 7-3-hour rotation cycle, surface temperatures likely vary by hundreds of degrees, creating thermal stresses that could contribute to gradual fragmentation or surface modification over long timescales. Radio observations fail to detect any modulation of signals that might correspond to the rotation period, eliminating exotic scenarios involving artificial or technological origins. The object spins silently through space. Its only communication with Earth, the ancient language of reflected sunlight, carrying information about surface composition and geometric structure. Yet, even this passive radiation tells stories about processes occurring in distant stellar systems, migration patterns of objects through interstellar space, and the physical properties of matter that has survived million-year journeys between the stars. Only took 7 hours and 18 minutes for each complete revolution to reveal its secrets. Only needed the mathematics of light and shadow to decode its three-dimensional form from two-dimensional observations. Only left behind the mystery of how such precisely timed tumbling could preserve itself across the vast emptiness of interstellar space. The story of Oumuamua begins in darkness, in the cold outer reaches of a planetary system orbiting a star whose light has never reached human eyes, perhaps 10 million years ago. Perhaps 100 million. This object condensed from the primordial disk of gas and dust that surrounded its parent star during the chaotic epoch of planet formation. In that distant system, Oumuamua may have been one of countless planetesimals, the building blocks of worlds slowly accreting material through gentle collisions in the gravitational nursery where planets are born. The young planetary system experiences the violent reshuffling common to stellar nurseries across the galaxy. Massive planets migrate inward and outward under gravitational influences, their orbital dance destabilizing smaller bodies throughout the system. Jupiter-sized worlds scatter asteroids and comets like cosmic billiard balls, sending some crashing into forming terrestrial planets, while ejecting others entirely from the gravitational embrace of their birth star. Oumuamua finds itself among the exiles, flung outward by a close gravitational encounter that accelerates it beyond the escape velocity of its original home. The ejection event itself unfolds over a matter of days or weeks, but its consequences span geological time. As Oumuamua crosses the boundary into interstellar space, it carries with it chemical fingerprints of its origin system, isotopic ratios of carbon, nitrogen, and oxygen that formed under the specific conditions of its parent star's nebular disk. These elemental signatures become frozen into its structure, preserving information about stellar nucleosynthesis processes and planetary formation conditions in a stellar environment that may differ substantially from our own solar system's history. Dr. Alan Fitzsimmons at Queen's University Belfast leads theoretical studies of Oumuamua's probable origin story, his team running computer simulations that model the ejection of small bodies from planetary systems throughout the galaxy. Their calculations suggest that every star system produces vast numbers of interstellar wanderers during its early formation phase, when massive planets settle into stable orbits and gravitationally scatter the remaining debris of planet formation. The Milky Way galaxy thus contains a vast population of nomadic objects, orphaned planetesimals drifting between stars, carrying within their physical structure the chemical heritage of their diverse birthplaces. The interstellar journey begins with Oumuamua moving at perhaps 5 to 10 kilometers per second relative to its parent star, fast enough to escape but slow compared to the velocities it will eventually achieve. As it travels outward through the gravitational influence of its birth system, the object experiences a final acceleration boost, gaining additional speed that will determine its ultimate trajectory through the galaxy. This gravitational slingshot effect, similar to the techniques used by spacecraft navigating the outer solar system, provides Oumuamua with the velocity needed for true interstellar travel. Once free of its parent star's gravitational well, Oumuamua enters the vast emptiness between stellar systems, where matter exists at densities billions of times lower than the best laboratory vacuum achievable on Earth. The interstellar medium consists primarily of hydrogen atoms and dust grains, with occasional molecular clouds providing slightly denser regions of gas and microscopic particles. Through this tenuous environment, Oumuamua travels in nearly straight-line motion, its path curved only by the weak gravitational influences of distant stars encountered during its million-year odyssey. The surface of the object undergoes gradual modification during its interstellar voyage. Cosmic rays, high-energy particles, accelerated by supernova explosions, and other violent processes bombard Oumuamua continuously, slowly altering its chemical composition through nuclear reactions that create new isotopes and break down complex molecules. Solar wind particles from distant stars contribute additional radiation damage, while ultraviolet light from hot blue stars along its path gradually darkens and reddens organic materials on the surface. These space-weathering processes operate so slowly that their effects accumulate only over millions of years, creating the mature, reddened surface that astronomers observe today. Gravitational encounters with other stars provide occasional perturbations to Oumuamua's trajectory. Though such close approaches remain rare during typical interstellar journeys, when they do occur, these stellar encounters can significantly alter both the object's velocity and rotation state, potentially explaining the complex tumbling motion observed during its passage through our solar system. Computer models suggest that Oumuamua has likely experienced one or two moderately close approaches to other stars during its interstellar wandering, each encounter leaving its signature in the object's current mechanical state. The temperature during interstellar travel hovers near absolute zero, perhaps 10 to 20 degrees above the cosmic background radiation temperature that permeates all of space. At these extreme cold conditions, Any volatile materials that survive the ejection from Oumuamua's parent system would freeze into solid form, creating a kind of primordial time capsule, preserving information about the chemical composition of its birth environment. Yet, the object shows no signs of such volatiles today, suggesting either that they were lost during the ejection event or subsequently removed by space weathering processes during the long interstellar journey. Navigation through the galaxy follows the gravitational architecture established by the Milky Way's spiral arms and central bulge. Oumuamua's trajectory carries it through regions of varying stellar density, from the sparse environments between spiral arms to the more crowded stellar neighborhoods closer to the galactic plane. Its current velocity of 26 kilometers per second relative to the Sun reflects not only its ejection speed, but also the accumulated gravitational influences of every massive object it has encountered during its cosmic wandering. The statistical analysis of Oumuamua's motion through local stellar neighborhoods suggests it has traveled roughly 50 to 100 light-years since its ejection, visiting the gravitational spheres of influence of perhaps a dozen different star systems during its journey. Each passage through another stellar system provided opportunities for additional gravitational modification of its trajectory, gradually randomizing its motion until its current path bears little resemblance to its original ejection vector from its parent star. Only took 10 million years of patient travel through the cosmic void to reach our solar system. Only needed a few gravitational encounters to erase most traces of its original orbital motion. Only preserved in its chemical composition and physical structure the faint signatures of processes that occurred in a planetary system now lost to astronomical observation. The acceleration begins as a whisper in the data, a subtle deviation from the perfect gravitational predictions that should govern Oumuamua's motion through the solar system. Dr. Marco Micheli at the European Space Agency first notices the discrepancy in June 2018, 8 months after the object's discovery. When precise astrometric measurements reveal that Oumuamua is not exactly where Newton's laws suggest it should be, the deviation measures only 40 micro-arc-seconds per day, an angular displacement so small it would take 70 years to equal the apparent width of a human hair held at arm's length. Yet this tiny acceleration carries profound implications for understanding the nature of interstellar visitors. Comets routinely exhibit non-gravitational accelerations as they approach the Sun, their surfaces heating and releasing jets of gas that act like miniature rocket engines, nudging the parent body in directions determined by the orientation and timing of the outgassing. But Oumuamua shows no visible signs of such activity, no coma of gas and dust, no tail streaming away from the Sun, no spectroscopic evidence of water vapor or other volatile materials sublimating from its surface. The acceleration vector points away from the Sun with mathematical precision, suggesting a radial force that strengthens as Oumuamua approaches perihelion and weakens as it recedes. This pattern matches the thermal forcing expected from sublimating volatiles, yet all attempts to detect the expected gas production fail to find any evidence of outgassing. Observations with the Spitzer Space Telescope, sensitive to the infrared heat signatures that should accompany sublimating ices, reveal no thermal emission beyond what would be expected from an inert, rocky object absorbing and re-radiating solar energy. Dr. Alan Fitzsimmons coordinates ground-based spectroscopic observations from multiple observatories, searching for the emission lines of water vapor, carbon monoxide, or carbon dioxide that should accompany any significant outgassing. His team employs the most sensitive detection techniques available, pushing the limits of current instrumentation to search for even trace amounts of gas production. The non-detections they obtain place stringent upper limits on any possible volatile release limits, so low that conventional comet-like outgassing cannot explain the observed acceleration. The magnitude of the acceleration itself provides clues to the underlying physical process. at its peak, near perihelion. Oumuamua experiences a non-gravitational force roughly 10,000 times weaker than Earth's surface gravity, barely sufficient to lift a grain of sand, yet persistent enough to accumulate into measurable trajectory changes over the months of observation. This gentle but sustained pushing suggests a process operating across the entire illuminated surface rather than localized jets of the type observed on active comets. Computer models attempt to reconcile the observed acceleration with various physical mechanisms that might operate on an interstellar object encountering solar heating for the first time in millions of years. Thermal recoil affects the momentum carried away by infrared photons re-radiated from the heated surface prove too weak by several orders of magnitude to explain the observations. Solar radiation pressure, which can influence the motion of lightweight objects in space, similarly falls short of accounting for the measured acceleration unless Oumuamua possesses an impossibly low density. The acceleration reaches its maximum strength when Oumuamua lies approximately 0.4 astronomical units from the Sun, well within the orbit of Mercury, where surface temperatures should exceed 300 degrees Celsius on the sunlit side. At these temperatures, water ice should sublimate vigorously, producing easily detectable gas clouds around any comet-like nucleus. The absence of such activity, combined with the clear evidence of non-gravitational acceleration, creates a fundamental paradox that challenges conventional understanding of small solar system bodies. Theoretical studies explore increasingly exotic explanations for the anomalous motion. Perhaps Oumuamua represents a fragment of a larger body that was disrupted during its interstellar journey, with internal structure or composition unlike anything found in our solar system. Perhaps it contains volatile materials that sublime at temperatures lower than typical cometary ices, producing gases too tenuous for current detection methods, but sufficient to generate the observed acceleration. Perhaps the object's extreme elongation creates unusual thermal or electromagnetic effects that concentrate outgassing along specific geometric axes. The rotation of Oumuamua complicates efforts to model the acceleration mechanism. The object's 3-hour tumbling motion should cause any directional outgassing to average out over multiple rotation cycles, producing little net acceleration unless the gas release is strongly concentrated along specific parts of the surface or aligned with particular geometric axes. Detailed thermal models suggest that the most effective configuration would involve outgassing from the object's ends rather than its sides, where the extreme elongation would create the largest temperature gradients and most efficient volatile release. Radio observations with the Green Bank telescope and other facilities continue to monitor Oumuamua for any emissions that might reveal the composition of outgassing materials. The search extends across multiple frequency bands, looking for the characteristic signatures of common volatile molecules as well as more exotic possibilities. The radio silence that emerges from these observations eliminates many conventional explanations while deepening the mystery of this interstellar visitor's anomalous behavior. Attempts to fit the acceleration data with theoretical models of comet-like activity require gas production rates so low that they approach the threshold of physical detectability. Yet even these minimal outgassing scenarios struggle to match the precise timing and magnitude of the observed acceleration without invoking unusual compositions or geometric configurations unlike any known solar system object. The mathematical models converge on solutions that seem to require Oumuamua to possess properties that are simultaneously conventional enough to explain its basic orbital motion, yet exotic enough to account for its paradoxical acceleration. As Oumuamua continues its outward journey beyond the orbit of Jupiter, the acceleration gradually weakens and eventually becomes undetectable as decreasing solar heating reduces whatever process drives the anomalous motion. The final astrometric observations, obtained in late 2018 when the object has faded to the limits of even the largest telescopes, confirm that the acceleration follows the expected pattern of a thermally driven process, strengthening near perihelion and fading with increasing solar distance. Only took the most precise astrometric measurements in astronomical history to detect the subtle deviation from gravitational motion. Only needed 8 months of careful position tracking to confirm that Oumuamua was gently pushing itself through space by some invisible mechanism. Only left behind the puzzling question of how an apparently inert rocky object could accelerate like a comet without showing any signs of the gas production that should power such motion. The absence haunts the observations like a missing note in a cosmic symphony. Every telescope turned toward Oumuamua searches for the familiar signatures of cometary activity, the glowing coma of gas and dust that should surround any icy body releasing volatiles near the sun. Spectroscopes scan for the emission lines of water vapor, carbon monoxide, and methane that mark active sublimation from heated surfaces. Infrared detectors probe for the thermal signatures that accompany gas production. Camera after camera captures images of empty space around the object, finding only the stark point of light that marks Oumuamua's position against the background stars. Dr. David Jewett at UCLA coordinates some of the most sensitive searches for cometary activity, employing techniques refined through decades of studying the solar system's most distant and faintest comets. His team uses the Hubble Space Telescope to photograph Oumuamua at multiple wavelengths, stacking dozens of images to reach the theoretical limits of detection for any possible coma or tail. The composite images reveal nothing beyond the expected scattered light from the object itself, no extended halo of gas, no streamer of dust particles carried away by solar radiation pressure, no asymmetric brightness distribution that might indicate directional outgassing. The non-detection becomes more puzzling when compared to the behavior of known comets at similar distances from the Sun. Objects like Comet 67P Churyumov-Gerasimenko, studied in detail by the European Space Agency's Rosetta mission, begin showing detectable gas production at distances of 3 to 4 astronomical units from the Sun, well beyond Oumuamua's closest approach. By the time such comets reach the orbit of Mars, they typically display obvious comas visible even to modest ground-based telescopes. Oumuamua passes nearly twice as close to the Sun as Mars, yet remains stubbornly inactive to all observational tests. Theoretical calculations of the expected outgassing rate, based on Oumuamua's size and the solar heating it experiences, suggest that even a modest fraction of ice on its surface should produce detectable gas clouds. Computer models of cometary nuclei indicate that objects need only a few % ice content to show obvious activity when heated to the temperatures Oumuamua encounters during its solar passage. The absence of any detectable coma implies either an ice content below 0.1%, extraordinarily low even for asteroid-like bodies, or some mechanism that prevents normal sublimation despite the presence of volatile materials. The search extends beyond visible light into other portions of the electromagnetic spectrum where outgassing signatures might appear. Radio telescopes monitor Oumuamua for the microwave emissions characteristic of water vapor and other simple molecules. Infrared observations probe for the thermal signatures of sublimating ices and the microscopic dust particles they carry along during release. X-ray and ultraviolet observations search for the fluorescence signatures produced when solar radiation ionizes gas molecules in a tenuous coma. Each observation technique yields the same result: no detectable evidence of gas or dust production. Dr. Alan Fitzsimmons leads efforts to place quantitative limits on any possible outgassing from Oumuamua, pushing observational techniques to their sensitivity limits to constrain the rate of volatile release, his calculations suggest that gas production would need to be at least 100 times lower than typical comets to remain undetected by current instruments. Such minimal outgassing rates approach the theoretical threshold where individual molecules sublimating from the surface might not form a coherent coma, instead dispersing immediately into the vacuum of space without creating detectable concentrations around the parent body. The acceleration data provides an independent constraint on outgassing rates, since the magnitude of the non-gravitational force must match the momentum carried away by any escaping gases. Detailed analysis of Oumuamua's trajectory suggests gas production rates of perhaps a few kilograms per second at perihelion, substantial enough to affect the object's motion, but apparently too small to create detectable atmospheric signatures around the nucleus. This creates a narrow window of physical conditions where outgassing can influence orbital motion without producing observable comas. Attempts to model the outgassing geometry focus on configurations that might concentrate gas release into highly directional jets rather than the diffuse, spherically symmetric patterns typical of most comets. Perhaps Oumuamua's extreme elongation creates preferential outgassing from its ends, where thermal gradients are steepest and volatile materials might be most concentrated. Perhaps the object's complex rotation causes gas release to occur in brief, intense bursts aligned with specific orientations relative to the Sun, creating jets too narrow and sporadic for current detection methods. The composition of any hypothetical outgassing materials remains completely unknown, opening possibilities for exotic volatile species that might sublime at lower temperatures or produce gases invisible to conventional detection techniques. Molecular hydrogen, for instance, lacks the strong emission lines that make water vapor and carbon dioxide easily detectable in astronomical observations. Carbon-based molecules might photodissociate so rapidly in the solar environment that they never accumulate into detectable concentrations, despite continuous production from the surface. Temperature mapping of Oumuamua's surface, based on its rotation period and thermal properties inferred from observations, suggests that different parts of the elongated object experience dramatically different heating rates as it tumbles through space. The ends of the object, receiving direct solar illumination for only part of each rotation cycle, might reach temperatures sufficient for sublimation only during brief windows of optimal orientation. This temporal concentration of heating could produce episodic outgassing that averages to very low rates over complete rotation cycles. Comparison with the handful of other asteroids known to exhibit weak cometary activity, objects like 3200 Phaethon and 6478 Gort, reveals that Oumuamua's behavior represents an extreme case even among these unusual hybrid objects. These transitional bodies typically show at least some detectable dust production, even if gas emission remains below detection thresholds. Oumuamua appears completely inert to all observational tests except the subtle astrometric signature of its non-gravitational acceleration. The paradox deepens when considering the object's apparent surface composition, which spectroscopic analysis suggests resembles the organic-rich materials found on dark asteroids and outer solar system bodies. Such surfaces typically contain volatile-rich compounds that should readily sublime when heated to the temperatures Oumuamua experiences during its close solar passage. The mismatch between expected surface chemistry and observed behavior suggests either unusual thermal properties that inhibit normal sublimation or compositional differences not detectable through current spectroscopic techniques. Only took the most sensitive astronomical instruments available to confirm the absence of any detectable outgassing. Only needed the mathematical relationship between force and momentum to prove that invisible gases must be escaping despite their observational silence. only left astronomers with the puzzle of an object that behaves like a comet while appearing completely inactive to every technique designed to detect cometary activity. The scientific community begins to grapple with Oumuamua's contradictory nature through a proliferation of theoretical models, each attempting to reconcile the object's comet-like acceleration with its asteroid-like appearance. Research groups across multiple continents develop competing hypotheses, their papers appearing in rapid succession as astronomers race to explain the first interstellar visitors' puzzling behavior. The models range from conventional extensions of known physics to exotic scenarios that push the boundaries of current understanding about small body composition and evolution. Dr. Darrell Seligman at the University of Chicago proposes that Oumuamua might consist largely of hydrogen ice, a form of frozen molecular hydrogen that could sublime invisibly while providing the thrust needed to explain the observed acceleration. Hydrogen ice forms only under the extreme cold conditions of interstellar space, where temperatures hover just a few degrees above absolute zero. Such material would remain stable during the million-year journey between stars, but begin sublimating rapidly when heated by solar radiation during passage through the inner solar system. The hydrogen hypothesis elegantly addresses several puzzles simultaneously. Molecular hydrogen gas is virtually invisible to most astronomical detection methods, lacking the strong emission lines that make water vapor and other molecules easily observable. The sublimation of hydrogen ice would produce a gentle, sustained thrust that could explain Oumuamua's acceleration without creating any detectable coma or tail. The low density of hydrogen ice might also account for the object's unusual strength-to-weight ratio, allowing it to maintain structural integrity despite rapid rotation. Computer simulations of hydrogen ice sublimation suggest that Oumuamua would need to be composed of roughly 50% hydrogen ice to generate the observed acceleration while remaining undetectable to current instruments. This composition implies formation in an extremely cold environment, perhaps in the outer regions of a planetary system where temperatures never exceeded 20 degrees Kelvin. Such conditions exist beyond the orbits of ice giant planets, in the realm of scattered disk objects and long-period comets that rarely approach their parent stars. Alternative theories focus on the possibility that Oumuamua represents a fragment of a larger body disrupted during its interstellar journey or shortly before its ejection from its parent system. Dr. Yun Zhang at the Laboratoire Lagrange in France develops models of tidal disruption events, where close encounters with massive planets or stars could fragment larger objects into elongated shards like the one observed. These fragmentation scenarios might expose fresh, volatile-rich material from the interior while creating the extreme aspect ratio observed in Oumuamua's shape. The fragmentation models suggest that freshly exposed interior material might contain volatile species different from those typically found on comet surfaces. Subsurface layers, protected from space weathering during the interstellar journey, could preserve primordial ices or organic compounds that sublime at lower temperatures than conventional cometary materials. The exposure of such materials during a recent fragmentation event might explain why Oumuamua shows evidence of outgassing despite its apparently inactive surface. Dr. Avi Loeb at Harvard University explores more speculative possibilities, suggesting that Oumuamua's acceleration might result from radiation pressure acting on an unusually lightweight or geometrically optimized structure. Solar radiation carries momentum that can influence the motion of objects with high surface area to mass ratios, similar to the way light pressure affects the motion of spacecraft equipped with solar sails. For radiation pressure to explain Oumuamua's acceleration, the object would need to be either extremely thin, perhaps a flattened sheet only meters thick, or composed of material with unusually low density. The radiation pressure hypothesis leads to exotic structural models where Oumuamua might represent a thin, sail-like object tumbling through space. Such configurations could arise naturally through tidal disruption of larger bodies, where gravitational forces stretch and flatten material into pancake-like shapes. Alternatively, the object might represent a fragment of a larger disrupted body that retained an unusual geometry optimized for interaction with electromagnetic radiation. Thermal stress models, developed by teams at the University of Maryland and elsewhere, explore whether repeated heating and cooling cycles during Oumuamua's journey might have created internal fractures that facilitate outgassing at lower temperatures than normal sublimation. The extreme temperature variations experienced during rotation from direct solar heating to shadowed regions near absolute zero could create thermal fractures that expose subsurface volatiles to space. These fractures might act as conduits for gas release while remaining too small to affect the object's overall structural integrity. The fracture models suggest that Oumuamua's elongated shape might actually enhance thermal stress effects. Since the extreme aspect ratio creates large temperature gradients between sunlit and shadowed regions, computer simulations indicate that objects with length-to-width ratios greater than 5:1 experience thermal stresses that can exceed the tensile strength of typical rocky materials, potentially creating networks of microscopic fractures that facilitate volatile release without visible outgassing. Compositional models focus on the possibility that Oumuamua contains unusual mixtures of materials not represented in our solar system's inventory of small bodies. Dr. Jennifer Bergner at the University of California, Berkeley, investigates whether irradiation of organic-rich surfaces during interstellar travel might create volatile species that sublime at temperatures lower than typical cometary ices. Cosmic ray bombardment over millions of years could gradually convert stable organic compounds into more volatile derivatives that would begin outgassing when Oumuamua first encounters significant solar heating. The irradiation model suggests that space weathering processes operating during interstellar travel might actually create rather than destroy volatile materials. Contrary to conventional expectations, high-energy cosmic ray particles could break chemical bonds in complex organic molecules, creating smaller, more volatile fragments that remain trapped within the porous surface structure until heated by solar radiation. This process might explain why Oumuamua shows no obvious signs of ice-rich composition, yet exhibits behavior consistent with volatile outgassing. Statistical analysis of Oumuamua's properties relative to known solar system objects reveals that several of its characteristics, extreme elongation, rapid rotation, anomalous acceleration, lie at the extreme ends of observed distributions. Dr. Matthew Knight at the University of Maryland argues that this clustering of unusual properties suggests either a formation mechanism fundamentally different from processes operating in our solar system, or post-formation modification during the interstellar journey that has no equivalent among gravitationally bound objects. The convergence of multiple unusual properties in a single object raises questions about whether Oumuamua represents a typical interstellar visitor or an exceptional case that happened to be the first detected. Computer simulations of interstellar object populations suggest that most such visitors should resemble conventional asteroids or comets, with only a small fraction exhibiting the extreme characteristics observed in Oumuamua. The discovery of additional interstellar objects will provide crucial tests of whether such unusual properties are common or rare among nomadic bodies traveling between stars. Only took the imagination of dozens of research teams to generate plausible explanations for Oumuamua's mysterious behavior. Only needed the application of known physics pushed to extreme limits to account for its contradictory properties. Only left the